Okay, so in this video we are going to discuss about single phase AC circuits. Single phase AC circuits, in that pure R circuit, pure L and pure C, and combination RL, RC and RLC series circuits. So first, what is single phase AC circuits? So single phase AC circuit is a simplest type of AC circuits which will be used in a home appliances and low load commercial applications. So this voltage from the single phase commonly in India will be 230 volt and the frequency will be 50 hertz. So in single phase representation, we represent voltage as V equal to Vm sin omega t and I equal to Im sin omega t. So we'll discuss in this video about a pure R, pure L and pure C circuits. So first, pure resistance circuits. So what is that pure resistance, pure inductance and pure capacitance will be? Means here we are going to discuss about what is a power factor, means what is that, whether it will be consuming power or it will store the energy, that we are going to discuss. For example, pure resistor. In pure resistor, voltage and current both will be in phase. In phase in a sense, the angle will be 0. If angle is 0, normally we define power factor as cos phi. Phi, if it is 0, then power factor will be 1. Means maximum efficiency will be provided by the pure resistive circuits. If it is pure inductance and pure capacitance, it will be means the power, the voltage and current. If we see the angle, means sometimes what happens is for example, in pure inductance, the current lags the voltage by 90 degree. In a pure capacitor, leads the voltage by 90 degree. So that 90 degrees is, so cos 90 will be 0. Means the power factor is 0 here. Means the resistor consumes the energy simultaneously. Means in positive as well as in a negative half cycle. But in a inductor and capacitor, the means the inductor and capacitor doesn't consume the power. It stores and it releases the energy. So that we are going to discuss it through the derivations. So first we are going to discuss about the pure resistance circuits, means a circuit without any combination, means only the resistance will be present in a circuit across the 230 volt AC supply. So we'll see pure resistance circuits now. So AC through a pure resistance. So the circuit, if we see, it's a simple circuit. There is a voltage source which is Vm sin omega t. We represent it as a Vm sin omega t. And here we consider it as a first equation. And the simple circuit with only resistor. So voltage is V and current through that voltage, current through the circuit is considered as a I. And the element which is a pure resistance. So let us consider AC circuit with a pure resistor R, and the unit of resistance is ohms, which is connected across the voltage, and we represent or we write V as Vm sin omega t in a single phase AC supply. So because of voltage, there will be a current I in the circuit. So how to represent voltage or how to relate voltage and current? It's by using the Ohm's law, because since there is only a resistance in the circuit, we use Ohm's law. So V is proportional to I. Ohm's law is nothing but V proportional to I, and R is constant. R is a resistance. So the second equation comes as V equal to I into R. And next we are going to substitute a V in this second equation. So what happens here? If V equal to Vm sin omega t, then Vm sin omega t equal to I into R. This is the previous second equation. And from this equation, I can write what is I. I equal to Vm by R sin omega t. Vm by R is a constant here with respect to omega t. So I equal to Vm by R sin omega t, and I can write this Vm by R. What is it? Vm is maximum voltage. If we consider the input as a sinusoidal signal, Vm is a maximum voltage. So Vm divided by the value of resistance sin omega t. So I can write this ratio Vm by R as Im. Im is a maximum amount of current. So I equal to, I can substitute Im in the place of Vm by R. So it is Im sin omega t. So the equation in a pure resistor for the I is I equal to Im sin omega t and V equal to Vm sin omega t. If we compare this I and first equation, there is no phase differences. V equal to Vm sin omega t, it means there is no angle difference. Omega t, usually the equation comes as omega t plus phi. In the place of phi, here it is 0. So even in I equal to Im sin omega t. plus 0. So both are in phase. So Im we substituted as Vm by R. So consider this as a fourth equation. So we have an equation for V and I, and there is no phase difference, means phi equal to 0. It means both voltage and current are in phase with each other. And next we'll see the waveform, means the voltage and current waveform, and the vector diagram of the pure resistor circuits. So first we'll see the waveform for voltage and current. So this y-axis is for voltage, current, and the x-axis with respect to t. And we consider only one cycle, because the same whatever the current and voltage, that repeats in all the other cycles. So we are considering one full cycle, which is 0 to 2 pi. So 0 to pi is a positive half cycle and pi to 2 pi is a negative half cycle. So this waveform, which is for the V equal to Vm sin omega t, and this smaller amplitude waveform, which is for the I, because I is Vm divided by R. So the amplitude of the current is small compared to the voltage. And if we see the phase difference, it's 0. We have Vm sin omega t and Im sin omega t. So both are in phase. So there is no phase differences. Both the voltages and current are in phases. This is the waveform for the pure resistor, and this is the vector diagram for the pure resistor. We take reference as voltage, and in that the current. Both are in phase. So voltage versus current, this is a vector diagram. So remember, in a pure resistor, voltage and current are in phase. And next, power in a pure resistive circuit, means whether it will consume power or whether it will store the energy and release the energy, that we are going to discuss it in a derivation. So voltage and current are changing at every instant. And power, the general formula for power is V into I, the product of voltage and current. And we know what is V, which is Vm sin omega t, and what is I, Im sin omega t from the previous slide. So substituting here, and we get Vm Im sin omega t into sin omega t is sin squared omega t. And we have a trigonometric formula for sin squared theta, which is 1 minus cos 2 theta divided by 2. So in the place of theta we have omega t. So 1 minus cos 2 omega t divided by 2. So if we split this equation, means here we have two terms, 1 and cos 2 omega t, and this is a product. So what I am going to do is, I am going to split this equation. One is Vm Im divided by 2, and one more is Vm Im cos 2 omega t divided by 2. And if we see this equation, this is a higher frequency, means we have input is just omega t, means Vm sin omega t, but here if we see it's 2 omega t, means double frequency. So we are going to neglect this second term, means this is nothing but the fluctuating component, because the frequency is doubled here. And we are going to consider only the first term, which is P equal to Vm Im divided by 2. I hope you understand. So this equation is nothing but the equation from the previous. Here I have splitted it into two terms. One is Vm Im divided by 2, and one more is minus Vm Im cos 2 omega t divided by 2. So this is constant power, means without any fluctuation, and this is a fluctuating component which is having the frequency double. And this is P. And next we are going to find the average power, because we are considering only one cycle, 0 to 2 pi. So what is the average power in that cycle, 0 to 2 pi? So P average. So P average formula, as we know, it's 1 divided by 2 pi, 0 to 2 pi, P into d omega t. 1 by 2 pi and 0 to 2 pi, which represents one full cycle, which is 0 to 2 pi, average. Normally what we do, the average of two numbers, it's like if you consider two numbers as A and B, then average will be A plus B divided by the number of components is 2. So A plus B divided by 2 we write. And here we are considering one full cycle, which is 0 to 2 pi. So the average, which is 1 divided by 2 pi and 0 to 2 pi and P into d omega t. And we have P from the previous equation. Okay, so equal to 1 divided by 2 pi, 0 to 2 pi, P, we are substituting these two components. Anyhow, we neglect this component because it will be high frequency. But here we are substituting it. Okay, so Vm Im divided by 2 minus Vm Im divided by 2 cos 2 omega t. A constant power with the fluctuating power with respect to d omega t. And next, we are going to integrate it with respect to omega t. So this 0 to 2 pi, 1 by 2 pi, 0 to 2 pi, which is common for both the terms. So we are separating it 1 divided by 2 pi, 0 to 2 pi, Vm Im by 2 d omega t minus second term 0 to 2 pi, Vm Im by 2 cos 2 omega t d omega t. We are neglecting this because it's highest frequency, or even we can say it is, if you integrate cos, then it will be sine. So sine 0 and sine 2 pi is anyhow it's 0. So this whole term will be cancelled. This whole term will be cancelled. So consider the first term, which is 1 divided by 2 pi, 0 to 2 pi, Vm Im divided by 2 d omega t. The integration with respect to omega t, so this Vm Im by 2 remains constant. So keep it out. So Vm Im divided by 2 into 2 pi, which is 4 pi, and 0 to 2 pi d omega t. Integration of dx is x. So integration of d omega t is omega t. And the limit is from 0 to 2 pi. Upper limit minus lower limit, which is 2 pi minus 0, which is 2 pi. 2 pi minus 0, which is 2 pi. And what happens is this pi and pi gets cancelled, and 2 and this 4 gets cancelled. So the remaining will be 2. So Vm Im divided by 2, and this we can write it as in terms of RMS. Vm divided by root 2, Im divided by root 2. Because root 2 into root 2 means root A into root A is A. So root 2 into root 2, anyhow we get it as 2. So splitting the term, and we are writing it as Vm divided by root 2, Im divided by root 2. This is nothing but RMS component of voltage and RMS component of the current. So writing it as a caps V into I. So average power equal to V into I, or P average equal to Vrms into Irms, where Vrms equal to Vm by root 2, Irms equal to Im by root 2. This is a power equation for the pure resistor circuit. And next we'll see about the power curve. And we already discussed about the waveform for voltage and current. So voltage and current both are in phase. So if you consider this voltage and current waveform here from the previous slide, here there is no phase and phase differences between voltage and current. So both the waveform passes through the same point. So we have two instant. One is 0 to pi and one more is pi to 2 pi. So we have two instant, 0 to pi and pi to 2 pi. So power waveform, which is P equal to V into I we got. So product of voltage and current. So if you see the first instant 0 to pi, whatever the voltage it isn't positive, and current value is also positive. So plus into plus is plus. The same concept we are going to use in this power waveform. So two instant, we are considering two instant, which is 0 to pi, and second one is pi to 2 pi. In the first instant 0 to pi, voltage is positive and current is also positive. Voltage is positive and current is also positive. So plus into plus will be plus. And power, which is a product of voltage and current. So amplitude will be greater than voltage and current. So you have to maintain maximum amplitude compared to voltage and current. And next, second instant, which is a negative half cycle of voltage and current. The voltage is negative and the current is negative. Minus into minus, which is plus. So power will be plus. And voltage is the same as the previous one, because only the cycle changes, the positive and negative value changes, but the amplitude remains same. So power waveform for the pure resistor is this. So voltage, which is Vm sin omega t, and current is Im sin omega t, and power, which is product of voltage and current, which is Vm Im sin squared omega t. So what we can understand here is power waveform, which is a sine square waveform, which is because sine squared omega t, and the voltage source is constantly delivering power to the circuit, which is consumed by the resistor, because here it doesn't go to 0. For positive half cycle also the power is positive, and negative half cycle also power is positive. And so the voltage source is constantly delivering the power to the circuit, which is consumed by the resistor. Therefore, the resistor consumes power. It doesn't store and release. It consumes the power constantly. This is about the pure resistor circuit. So next we'll see about the pure inductance circuits. So in the circuit there will be only one element, which is inductor, which is connected across the voltage source V. So the current is I, the voltage is V, and inductor is L here. So we are going to consider a magnetic field in this. because power stored and released to the magnetic field. So this is a simple circuit of pure inductance, and usual we write V as Vm sin omega t, and I is the current flow through the inductance. So what happens, since it is a coil, we consider a magnetic field. So when alternating voltage I flows through the inductance, it sets up alternating magnetic field around the inductance. So the EMF will be induced in the coil, and this EMF opposes the applied voltage. So what we write is V, which is applied voltage, V, which is equal to minus into E. V equal to minus into E, because voltage, whatever the EMF induced, that opposes the applied voltage. For that concept, V equal to minus E. So what is it EMF? EMF induced in the coil is E equal to, according to the self-inductance, it's not a mutual inductance, self-inductance, because it's only one coil is there. Mutual inductance between two coils. So here, since there is only one coil, we consider a self-inductance equation, E equal to minus L into di divided by dt. V equal to minus E. So first equation, which is V equal to Vm sin omega t, and second equation is for the EMF. Third equation is for the applied voltage, which is opposes the EMF induced in the coil. So substituting the third equation and the second equation, V equal to minus, what is E? L into di divided by dt, and minus into minus will be plus. So L into di divided by dt. So what is V according to the first equation? So V is Vm sin omega t, which is equal to L into di divided by dt. So we are going to find the relation between voltage and current. In the pure resistor, the relation between voltage and current was in phase. There is no phase differences between the two. Here we are going to find what is the difference. Is it in phase, or it leads, or it lags? So we have to get equation for the current I. So for that, we are keeping only di in one side. So di equal to, rest all the term goes to other side. So Vm divided by L sin omega t into dt. So keeping di in one side and taking the rest all to the other side. So L goes to denominator, dt goes to the numerator. So Vm by L sin omega t into dt. So di is there. To find I, we have to integrate on both the sides. So integrating di gives I. So I equal to Vm by L is a constant. Integration sin omega t into dt. So what is integration of sin omega t? Which is minus cos omega t divided by omega. Okay. So it's like sin integration of sin 2a. It's like minus cos 2a divided by 2. So constant comes down. So sin omega t with respect to t, no? The integration with respect to t. So omega is constant. So minus cos omega t divided by omega. So minus what we got in previous equation, Vm by L omega cos omega t, right? So the omega, if we take it out, so it will be Vm divided by omega L cos omega t. Okay, so we are rewriting that equation to get a format. We applied voltages V equal to Vm sin omega t. So to change it to that format, Vm by omega L cos omega t can be written as minus Vm divided by omega L cos omega t can be written as sin 5 by 2 minus omega t. Cos omega t can be written as sin 5 by 2 minus omega t according to this equation. We have an equation sin 90 minus theta equal to cos theta. Sin theta minus 90 means minus cos theta. So we have cos theta here. So cos theta in a sense sin 90 minus theta. 90 is 5 by 2. So cos omega t can be written as sin 5 by 2 minus omega t. So minus Vm by omega L sin 5 by 2 minus omega t. Okay. So I equal to Vm by omega. So what we have done is our mathematical representation comes as either V or I equal to Im sin omega t comes first. Omega t minus some angle. Omega t minus some angle. But here what we got is angle minus pi by 2 minus omega t we got. So to rearrange it, we are using one formula called sine of minus theta, which is minus sine theta. Okay, sine of minus theta, which is minus sine theta. So Vm by omega L sine of omega t minus 5 by 2. So minus will be plus. Okay, so I equal to Vm by omega L. This ratio can be written as Im sine omega t minus 5 by 2. So if you compare this voltage and current relation, voltage which is V equal to Vm sine omega t minus 0, right? Because nothing is there in the place of angle. So phi is 0. But here I we got it as Im sine omega t minus 5 by 2. So in angle which is pi by 2, and we got it as minus pi by 2. So what we say is the current lags the voltage by 90 degree, pi by 2. So Im we have substituted as Im in the place of Vm by omega L equal to Vm. What is omega L? Omega L is nothing but 2 pi Fl. Omega is angular frequency, which is 2 pi F into L. So 2 pi Fl, which is for the inductive reactance, XL equal to 2 pi Fl. So XL we can substitute as XL. So it is written over here. So XL is a inductive reactance. So inductive reactance, in a sense, it's a type of resistance offered by the inductor. Capacitive reactance, in a sense, a type of reactance offered to the capacitor. Okay. So the waveform, if we see the waveform for the voltage and current ka relation, if we see, it's a lagging by 90 degree. Which lagging? Current lags the voltage by 90 degree. Okay, lags in essence a delay. So voltage which is having the angle 0 degree, right? Vm sine omega t, in the place of angle nothing is there, so 0. So it starts at 0, 0, pi and 2 pi. But what about the current? It lags the voltage by some angle pi by 2. So if you see our positive half cycle, it starts from 0 and it ends in pi. Means 0 to 180 degree. What is the half of 180 degree? Which is 90 degree. So pi by 2 is here. So here the current starts. The current lags the voltage by pi by 2. So the phase difference here is 90 degree. So 90, it maintains the lagging of 90 degree in all over the cycle. So this is a waveform, voltage and current waveform for the pure inductor. And vector diagram, we consider the reference as a voltage and current lags the voltage by 90 degree. Okay, in this direction if you see, the current lags the voltage by 90 degree. So this is a vector diagram. And next we'll see the power. So power, which is V into I, P equal to V into I. What equation we got for V? Which is Vm sine omega t. And I we got it as Im sine omega t minus pi by 2. So we have to simplify and we have to find the power of pure inductance circuits. Okay. So Vm sine omega t, Im sine omega t minus pi by 2 can be written as minus Vm Im. What we are going to do is we are substituting the sine omega t minus pi by 2 as cos omega t. Okay. So minus Vm Im sine omega t cos omega t, which is equal to minus Vm Im sine theta cos theta. So 2 sine theta cos theta is sine 2 theta. 2 sine theta cos theta is sine 2 theta. So sine theta cos theta will be sine 2 theta divided by 2. So minus Vm Im sine 2 omega t divided by 2. Okay. This, I hope this you understand how that sine omega t minus pi by 2 is cos omega t. So this is from the previous, like whatever we substituted previously, we considered cos omega t as sine 90 minus theta, and later we substituted as minus sine theta equal to sine of minus theta. The same thing, because here to derive the power, we don't have the exact formula here. It will be very difficult. So we are to use this formula. We are rewriting it as sine omega t into cos omega t. sine 2 omega t divided by 2. So it will be easy to simplify it later. So minus Vm sine 2 omega t divided by 2. And next, to find the average power, like the previous derivation, P average equal to 1 divided by 2 pi, 0 to 2 pi, P d omega t. So 1 divided by 2 pi, 0 to 2 pi, in the place of P we are substituting it as minus whatever the previous equation. This we are going to substitute here. Minus Vm by 2 sine 2 omega t into d omega t. And here the constants are minus Vm divided by 2. That we are keeping it out. Minus Vm divided by 4 pi, 0 to 2 pi, sine 2 omega t into d omega t. Minus Vm by 4 pi, sine 2 omega t ka integration is minus cos 2 omega t divided by 2. Because integration with respect to omega t, so the 2 will be constant. So that comes in a denominator. Minus 2 cos 2 omega t divided by 2, 0 to 2 pi. Upper limit minus lower limit. So minus that we can keep it out. So minus, if we keep it out, then cos 2 into 2 pi, which will be 4 pi. So cos whatever the value is, n even or odd, the answer is means if it is odd, it will be 1. Even if it is even, the answer is 1. For example, cos 0 is 1, cos pi will be minus 1. So here cos 0, the lower limit is cos 0, so it is 1. Upper limit is cos 2 pi, which is even, so cos 4 pi. Cos 4 pi ka value is 1. So 1 minus 1 will be 0. So average power is 0. What is the meaning of this 0 answer is, the average power consumption is 0 we got. Means the inductance doesn't consume power. It stores and it releases. So in the positive half cycle it stores. In negative half cycle it releases the energy in a magnetic field. So how we can represent it in a power waveform? So that we are going to discuss here. So power waveform where we are considering voltage and current as a reference and we are finding what is the power, right? So if you see the previous waveform here, voltage and current, how many instants we have? We have 4 instants. We have 4 instants. One is 0 to 90 degree and second instant is 90 degree to 180 degree and third instant which is 180. Okay, 180 to 270 and next 270 to 360. 0 to 2 pi. The 4 instants we are getting 0 to pi by 2, pi by 2 to pi, pi to 3 pi by 2 and 3 pi by 2 to 2 pi. 4 instants. So all the 4 instants we are going to consider in this power waveform. So first instant is 0 to pi by 2. So what about the voltage? This is voltage curve which starts at 0 and this is the current. So voltage is positive, current is negative. Plus into minus, the power will be minus. So if the power is minus, then the meaning is power will be released in this cycle. And next instant pi by 2 to pi. So in this pi by 2 to pi, the voltage is positive. The voltage is positive, even the current is positive. Plus into plus is plus. And next third instant, pi to 3 pi by 2. In this instant, voltage is positive, voltage is negative, even the current is negative. Minus into, the voltage is positive, voltage is negative, the current is positive. The minus into plus is minus. So the power is minus here. And the last instant, 3 by 2 to 2 pi. So here, what happens with the voltage? Voltage curve is negative. This is voltage curve and this is a current curve. This is also negative. So minus into minus will be plus. So we are getting the negative power as well as positive power. So negative cycle ka power represents the release of power and positive. Okay, so it's about the pure capacitance circuits. So as we discussed in previous slides, pure resistor which is in phase means it consumes power. Pure inductance where the current lags voltage by 90 degree and it doesn't consume power, it stores and releases the energy. So we'll see about the capacitance circuits. So capacitance circuits, even it is a simple circuit with the capacitor which is connected across the single AC source supply, which is a voltage V. So capacitor, which is a parallel plate capacitor, as we know, it charges and discharges. So we'll see through the derivation like it doesn't consumes power, it only stores and releases the energy. So the V equal to Vm sin omega t, which is a voltage equation through a single circuit, single phase AC circuits, considered as a first equation. Since it's a capacitor element, we are going to discuss about the charging of the capacitor. So charge, which is Q, equal to C into V. The relation between voltage and the charges takes place as Q equal to C into V, and V we are substituted as a Vm sin omega t. So first and second equations are this. And next we have to find what is the relation between voltage and current. Is it lagging or leading or in phase? So for that, for the capacitor element, we are using the equation I equal to dq divided by dt. In the place of Q, we are substituting C into V, which is C into Vm sin omega t from the second equation. So C Vm sin omega t, and C Vm is a constant, and this is a differentiation with respect to t. So d by dt sin omega t rest to C Vm remains constant here. So differentiation of sin omega t, which is cos omega t. So omega C Vm cos omega t is the equation. So to get it in a general form, which is I equal to Im sin omega t plus some angle or minus some angle, we are rewriting the equation. So here the numerator omega c, that we can take it to denominator as 1 by omega c, which is nothing but omega Vm only, omega c Vm only. So Vm divided by 1 by omega c sin omega t plus pi by 2. This sin omega t plus pi by 2 comes from the formula cos theta equal to sin theta plus pi by 2. So in the place of theta we have omega t. So omega t plus pi by 2. So we are going to substitute Im in the place of Vm divided by 1 divided by omega c. So we get equation as I equal to Im sin omega t plus pi by 2. So if we see the relation between voltage and current, which leads the means we have the angle plus pi by 2, means the current leads voltage by pi by 2. Plus is there, so leads, minus means lagging. So Im, which is Vm divided by 1 by omega c. Omega is the angular frequency, which is 2 pi f. 1 divided by 2 pi fc is nothing but the capacitive reactance. So current leads voltage by pi by 2, means 90 degree. So we'll see the waveform. So as we know, V equal to Vm sin omega t, where the angle is 0. So it starts at theta equal to 0, time equal to 0, 0, pi and 2 pi. This is one cycle of voltage. The next current, which leads voltage by pi by 2. So it starts early. So minus pi by 2 to 0 is the first instant, and 0 to pi by 2 is the second instant in the positive half cycle of current. And if you see, this is the voltage and current waveform for the pure capacitance. And next we'll see the phasor diagram, and usually we take voltage as a reference, and current leads voltage by pi by 2 in this direction. So pi by 2, which is 90 degree. So current leads voltage by pi by 2. And next we are going to see, as it like previous, what is the power consumption in the pure inductance circuits. So for that we consider the general equation, which is P equal to V into I. V we got it as Vm sin omega t, and I is Im sin omega t plus pi by 2. So what is product of V and I, which is Vm Im sin omega t plus pi by 2. Sin omega t plus pi by 2 can be written as cos omega t from the previous equation. So Vm Im sin omega t cos omega t. So what is sin theta cos theta, which is sin 2 theta divided by 2. So sin 2 omega t divided by 2. So next we are going to find the average power for the first cycle, 0 to 2 pi. So 1 by 2 pi, 0 to 2 pi, P into d omega t. 1 by 2 pi, 0 to 2 pi, P is substituted as Vm Im sin 2 omega t divided by 2 into d omega t. Integration with respect to omega t. So Vm Im by 2 remains constant. So with that we are keeping it out. So Vm Im divided by 4 pi, 0 to 2 pi, sin 2 omega t into d omega t. So integration of sin 2 theta into d theta is minus cos 2 theta divided by 2. Because integration with respect to omega t, so 2 remains constant. So that comes as in a denominator. So minus cos 2 omega t divided by 2, 0 to 2 pi. And minus Vm Im divided by 4 pi into 2, which is 8. And upper limit is 2 pi and lower limit is 0. So cos 4 pi and cos 0, which is 1. So 1 minus 1 will be 0. So average power we got it as 0. Means the inductor doesn't consume power. It doesn't consume power. It stores, or we can say it charges and discharges in the electric field. And next we'll see the power waveform. So power waveform, for that we take voltage and current as a reference. So here there are 4 instants, which is 0 to pi by 2, and pi by 2 to pi, and next pi to 3 pi by 2 and 3 pi by 2 to 2 pi. So 4 instants are there. So as we know, power is a product of voltage and current. If voltage and current both are positive, then plus into plus is plus. If plus and minus, then plus into minus is minus. If it is minus and plus, then minus into plus is minus. If both are negative, then the power will be plus. So in that we get a power waveform like this, and the power which will be charged during positive half cycle and discharged during the negative half cycle. So it can be observed that when the power curve is positive, energy gets stored in the capacitor during charging, while the negative power curve represents that energy stored is returned back to the supply during its discharging. Therefore, pure capacitor and pure inductor doesn't consume or never consume the power. It just stores the energy and releases in the magnetic and the corresponding electric field. That's all about the pure inductance, pure capacitance and resistance. Thank you.